Okay, so there are few remaining topics that I want to cover in this frequency filtering, or in general the frequent filtering area. So one is this Laplacian filters that we will cover quickly. Then there are band pass and band reject filters. So I'm not going to go into too much detail of this. We have seen last time in the previous lecture, we saw some of these things in detail, right? So we looked at low pass and high pass filters, okay? So band pass and band reject filters are combinations of low pass and high pass filters. So I will just show you the plots, perspective plots of those filters and show you what they can do, okay? And then there are these two effects. So we have seen aliasing in one dimension. So I want to talk about aliasing in 2 dimension and Moir patterns, okay, also in 2 dimensions. So these 2 effects we will see, and we will see how they can be reduced, okay. So let's begin. Let's talk about the Laplacian filter. So we want to talk about it in the frequency domain. For that, I'm doing a small review of Laplacian in the spatial domain. So this is something we have done already. I'm just reviewing. Okay, so recall that it is obtained as the second derivative of the given image function. So if the image function you denote by fxy, then using finite differences, one can calculate the second derivative of f in the x direction and second derivative of f in the y direction, exactly using these formula. So these 2 together will give us the Laplacian of f. Okay, so this is the formula for the Laplacian. And if you just substitute the right-hand sides, you can see that this is the expression for the Laplacian. Now, this Laplacian can be implemented on an image using a kernel. Okay, so because these, you can see these are locations around xy. Right? So you have the pixel xy on which you want the kernel to act, and then these locations are exactly. So in this case, if your if the location is here, okay, if this is xy, then x plus 1. So this is x y, right? And so x minus these are all in integer increments. So then x plus 1 y is going to be here. X minus 1 y is going to be here. X y minus 1 is here, and x y plus 1 is here. Okay, so these are the locations. The f at these is the pixel values at these locations. Okay, so these 4 locations minus 4 times this. So if you want to implement the Laplacian on a function, on a image, you may implement it by applying this kernel to the image, right? So this we saw in detail in some earlier lecture. There are also other Laplacian kernels given in this way. Okay. This is simply by multiplying everything with a minus sign. You could take minus of this. And number 1 and 2, these 2 kernels are isotropic in rotations of 90 degrees. Right? If you rotate in both of these by 90 degrees, you will still have the same kernel. Now, you can make also an isotropic in 45 degrees kernel using a Laplacian, which is by also considering the diagonal directions. So you also look at the derivative in these directions and make up an expression like this. Okay. So in each of these directions, this term fxy will come twice. Okay? And so that is how this 8 will come up. So if you do a similar simplification with 8 directions, this is the sort of kernel it will correspond to. And with a minus sign, it is this. So these are your Laplacian kernels, and 1 and 2 are isotropic with respect to rotation in 90 degrees. 3 and 4 are isotropic with respect to rotation in 45 degrees also. Well, the effect of the Laplacian is to, if you want to enhance the sharp edges of an image, then you apply the Laplacian. Okay. But what the Laplacian will do is that it will blur out the slowly transitioning intensities. What this means is that where there are no edges, if there is a plane area, then the Laplacian is going to blur all those areas. and only bring out the sharp edges. So the reason why this happens is I have explained in detail in one of the earlier lectures where we describe the first and second derivatives along an intensity ramp of an image. Okay, so where I also described the zero crossings and everything. So in that lecture, it will be clear why this happens. Okay, but the result of this is that the edges and discontinuities are displayed properly, and everything else sort of darkens out. Okay, the rest of the image will darken out. So that is the effect of the Laplacian. And so if you display the resulting array as an image, that image is not most useful. Okay, so because everything else has darkened, that image is not very useful. The way to use the Laplacian is to add it back to the original image, because by adding back to the original image, in the original image, the edges and discontinuities will look sharper. Okay, so that usually it is done like this. So you have the input image, you take plus some plus or minus 1 times the Laplacian image that you get. Okay, so the result is an edge sharpened output. This C is plus or minus 1 depending on the sign of your kernel. Okay, so for example, if your kernel is of type 1 or 3, then you will use minus 1. Sorry, plus 1. Okay, you will add the result of the Laplacian if your kernel is 1 or 3, and subtract the result of the Laplacian if it is 2 or 4. Okay, so that is simply because the way what this addition does. Okay, or you can check what happens if you do it the other way. Okay, you will see that using these signs is what makes the image useful. Okay, so for example, here this is the image of the North Pole of the moon. This is the Laplacian. Okay, so you can see that the edges are coming out strongly. Okay, and whatever discontinuities, in the sense that wherever there are these small contours or edges, all that is also coming out strongly. Okay, but this part where there isn't much such there aren't such strong changes in intensity in this region, that region is simply being darkened or blurred out. Okay, so that is what the Laplacian does. And so you can see that the Laplacian itself displayed as an image is not a very useful entity. Okay, but now if you add these two, then you get an image like this, where if you now compare even visually the first image, the original image with this one, you can see that this has the edges are sort of, or this image has essentially been sharpened a bit. Okay, everything appears a bit sharper in this image. Okay, this is the one where only 4 neighborhood positions are used, and this image is obtained where 8 neighborhood positions are used. Okay, Laplacian with the kernel of type 3 or 4. Okay, so this image is being sharpened in this way. So you take the Laplacian, then you add it to the original image in this way, and you get a sharpened image. That is how one uses the Laplacian. Okay. Now this same image, actually, you might see displayed. Oops, you might see displayed in this way. Okay, this is nothing but the same image where the intensities have been spread over a larger range. Okay. Sorry, I don't know. I shouldn't be doing that. So sometimes you will see Laplacian displayed in this way also. It's just the original image with spread out intensities. Okay. All right, one point that I want to make here is that is to explain why over areas of intensities which are not moving too fast do we get this blurring or darkening. Okay, so this is a result of having a kernel such that the sum of all entries of the kernel is 0. Okay, so you'll see in all these the sum of all entries is 0. What happens because of that is that if you have an area where the intensities are either the same or they are not changing too much, okay, So if they are the same, then suppose you are doing this, you're filtering at a certain pixel. You're doing this computation or applying this mask over a certain pixel. Then what is going to happen is that when you do this, since all intensities over that window are the same, and now you're applying this kernel whose sum is 0, you will end up with a 0 at that spot. Or if the intensities are varying very lightly, then you will end up with a small number at the spot. And so that will darken the image. If you end up with a 0, you'll have a black pixel at that spot, and otherwise you will have a darker pixel at the spot. So essentially, if you have a kernel such that the sum of the entries of the kernel is 0, then this effect happens. Okay? Over an area of constant intensity or low varying intensity, the result of that kernel will be darker pixels. So that is something to note in general, and in particular, this is why the Laplacian is looking like this. Okay. All right. So this was the recap of Laplacian in the spatial domain. Now in the frequency domain, the Laplacian is implemented using this function. Okay, so earlier for every filter we saw what the functions HUV were. Similarly for the Laplacian, it is this, where d square UV is the same notation as before. It is the distance of UV from the center of the frequency rectangle. So this is the function that implements the Laplacian in the frequency domain. So as usual, you will calculate the Laplacian as the inverse Fourier transform of HUV times FUV. Once you have obtained the Laplacian, then you will do edge enhancement like I described in the spatial domain, which is by adding plus or minus 1 times the Laplacian to the original image. Okay, and the results will be, well, the results are going to be the same whether you perform in the spatial domain or you perform in the frequency domain. The image results will be the same. It is the efficiency in computation that makes you resort to the frequency domain computation. Okay. There's one small remark about using this frequency domain transformation for the Laplacian. It is observed that using DFT introduces some large scaling factors. So when DFT is applied to convert and to convert back, then you can have some scaling factors applied, which means that instead of fxy, you will have some scalar time fxy. Okay, which means that not scalar time fxy, you will have some scalars multiplied to this output, which means the Laplacian image will come out with some different intensity values than were there in the original image. Okay, so that is possible. So in order to do this addition, usually one applies normalization to both of these so that they are scaled down and then added. Okay. Now the Laplacian quantities can be, the pixel values can appear negative also. Okay, when you are doing a Laplacian. So then del f is scaled down to -1, 1. Okay, and fxy is scaled down to 0, 1, and then this addition is done. Okay, so that's the only difference. In the spatial domain, you don't need to do any such normalizing. But if you're applying Laplacian in the frequency domain, you need to be aware that this kind of normalizing may be required. Okay, so that is all about the Laplacian filter in the frequency domain. Next, what I want to talk about is this bandpass and bandreject filters. Just give me a moment. So these are examples of bandpass or bandreject filters. Bandpass essentially means that it will let a certain chosen band of frequencies pass, and bandreject will mean that it will reject a certain band of frequencies. Okay, and so typically Okay, so why are these all around? So if you remember, the frequency domain generally, well, we know that when we talked about shifting the origin, right? The origin is here, okay, but then we shift the origin to the center of the frequency rectangle. Okay, so the origin now is here for the frequency domain, and so because of those symmetry properties of uh, Fourier or the result of the Fourier transform, what happens is that in the frequency domain, the result of applying DFT appears in 4 places, right? So you see, whatever you see here will also appear in these 4, right? So that's how the frequency domain information looks like visually, right? That is why, so you see this symmetry in any image of a frequency domain applied to, of the frequency domain transform applied to any image, correct? So that is why all these filters that you see are centered around this origin, okay? Because then really what is happening here is important, and then because the same frequencies are appearing in all these, you just apply the same transformation in all these, and that is why all these filters appear circular, right? The Gaussian, Butterworth, or the ideal, all those perspective plots that we saw, they all appear circular because of this exact reason. Okay, so this is how the band reject filters or band pass filters will appear, because again you just need to process around this center of the frequency rectangle, right? So now the idea of band reject filters or band pass filters is that suppose you want certain frequencies in this region to pass, okay, then what you will do is you will block the frequencies here and you will block the frequencies outside this region. Okay, so then what will happen is with this filter only the frequencies appearing in this much band will be able to pass. So that's a band pass filter. Okay, and you could also have a band reject filter by subtracting this band pass filter from 1, in which case the exact opposite will happen, which is that you will have instead of having these frequencies being passed, okay, you will have the other way. You will have that these are being blocked, okay, and all other frequencies are passed. Okay, so yeah, maybe I said the name the opposite way. So if you choose a band and you are allowing the frequencies in that band to pass, this should be a band pass. Okay, you are allowing these frequencies to pass, so that's a band pass filter. And here you are blocking these frequencies, so this is a band reject filter. Okay, that's the basic idea of band pass and band reject. And one, if you have a formula for band pass, then a band reject filter will be 1 minus the corresponding band pass filter. That is the connection between the two. Okay, and these are their perspective plots. So in these case, these are all band reject filters. They are rejecting the bands of a certain width and then passing the rest of them. Okay. You can see that's what happening, right? Because in this band, you have 0, and in the rest of the spots there is 1. Okay, so the frequencies in this band are being rejected. So that's a band reject filter function. This one comes from the formula for ideal low pass filter. This comes from the Gaussian filter, and this comes from the Butterworth filter. So the perspective plots itself sort of tell you how the action is going to be. So these are very sharp filters, right? These are cutting off the frequencies very sharply. Whereas the Gaussian, this is sort of a smooth cutting off. So there is going to be a blur around these. So this is going to also not only reject some frequencies, but also cause some blurring. Okay, and this is going to cause more of a blur. This is almost like the Gaussian, but there is much more blur along all intensities. Okay, so that's what is going to be the difference between these. So if you look at the image, so this is just a perspective plot, but you have an array, right? So if you look at the image of the array, this is how the ideal bandpass filter will look like. This is the Gaussian bandpass, and this is the Butterworth bandpass. Okay, so these are the sort of effects they will also create. This will create blurring. This will create more of a blurring. Okay. So the use of when do we want to use a bandpass or band reject filter? One of the clear uses of these are in Moore patterns. Okay, so let me say what a Moore pattern is. Okay, so an effect that is created like this, because you have a certain pattern in the image and a certain other superimposing pattern. Okay, so if there are two patterns that are appearing at the same time, then it can appear, in fact, as a third pattern. This is called as a Moore effect. Okay, so this is not coming because of sampling or any other thing. This is simply because there are two distinct patterns which are joining together to make it appear like there is a third pattern. Okay, and so this kind of thing or this kind of effect can appear even with dots. So this is with lines, and the same thing they have shown with dots. Okay, so if there's a pattern, dot pattern like this and a dot pattern like this, together in the image, it can create a pattern like this. Okay, now this is called a Moore effect. So this is simply a geometric effect. This has nothing to do with sampling or anything. Okay, and an example of this is here. So this is something that is you must have seen in some newspaper or poor quality printing, that this kind of effect appears. Okay, so this is an example of a Moore effect or a Moore pattern. Okay, now the notch filter is works perfectly in this situation. So if the frequency, if this image is looked at in the frequency domain, okay, so this is its frequency spectrum. Okay, then one can see that there are these really, you just need to look at this quadrant. Okay, you know that whatever is going to be up here in this quadrant is going to be repeated in these three places also. Okay, so essentially you just need to look up here. Okay, and so this is telling us there are these two spots where there are really high frequencies. Okay, now one of the things that you could try is to block out these high frequencies. So when do high frequencies appear? So high frequencies appear when there are sharp changes between low intensities and high intensities between the pixels, right? So with that heuristic, one can try and block out these frequencies and see what happens in the image. Okay, so the way to block out these frequencies exactly is to use the notch filtering. Okay, notch filter will do what? It will block. So you put that notch filter of this size over this and block it out, which means in practice you're going to multiply with HUV, where HUV is the notch filter. Okay, so if you do that multiplication, which the output of that multiplication is shown here. So essentially these frequencies are blocked out. Because of symmetry, this is going to also appear everywhere. Okay, so these frequencies are blocked out, which means we are trying to block out these high transitions between low and low and high intensities in the image. Okay, and then that sort of removes or blurs the effect of this Moore pattern. Okay, so this is one way in which notch filtering is used. You can remove Moore patterns using notch filtering in this way. Okay, now this is one of the rare examples where one can actually clearly explain how you can do processing in this domain and obtain an image result like this. Okay, otherwise it is very difficult to just look at the spectrum and say what the entities in the spectrum correspond to in the image. Okay, so in general, in image processing, it is not a good idea to, we are usually used to doing processing on the actual image where the edges and the objects are seen. But if you see in the frequency spectrum, then nothing is seen. Okay, and then you don't know what to make of this line or this line. Okay, so there are few guidelines among the theory that can tell you what you can expect. When can you expect some sharp whites? Okay, so this, for example, the center is the average of all the pixels. That is one property that we have seen. Okay, so if the image is bright or there are some number of white pixels, so the brightness of this is going to depend on the average intensity of the image. Okay, so that is one sort of thing that we know. And this, or knowing that there are some intensity transformations that will cause these white dots along the spectrum. Okay, and if you block those out, then you will reduce some of the transitions and intensities in the original image. So that is one kind of thing that you can sort of glean from these examples. But otherwise, if you think that you can look at the spectrum and just by that you know that what every component of the spectrum means in the image and you can process that way, that is not necessarily true, because the spectrum doesn't give you any visual information about the image. Okay, so the main two ways in which one would use the frequency information, okay, is one, all the spatial filters. Spatial filters you can visualize. You can look at the image and you can know what you want to do, correct? So the spatial filter is something you can very much visualize. You use the frequency domain idea to reduce the number of computations. Okay, you don't think that you will be able to look at the image and make some meaning out of it. Rather, you just use it to reduce the number of computations. That is one way. And the other way is sometimes, this kind of information, if you block out, you can get some kind of restoration or some kind of enhancement of the image. Okay, but it requires considerable practice to be able to go back between the information that is presented in the spectrum or presented in this frequency image and what it should mean in the original image. Okay, so that is not a one-to-one correspondence, or it's not an easy dictionary between these two. Okay, so that is something that you have to keep in mind. All right, so coming back here, so that was about power pattern. The other effect that you should be aware of is aliasing. So aliasing is something that we talked about in 1D, right? So I have shown you examples of aliasing in 1D and why it happens. So the main reason why aliasing happens is that sampling is done at lower frequency. Okay, so you don't have undersampling because of undersampling, right? That is the reason for aliasing. So here is a 2D example of it. Okay, so down here this is the sampling grid. Okay, so this is some fixed sampling is there, and they have shown you what happens with 3 different kinds of signals. So if your sampling grid is receiving a low frequency signal, okay, then so this is what the original signal looks like. Okay, and when it is sampled, this is what it is going to look like. Okay, so this you can think of this is going to be the sampled signal, while this is the original signal. Okay, so then in the sampled signal, you see that the edges are going to be slightly jagged. Okay, but it's not too bad. You can still sort of make out what the original signal might be. Okay. Now, if the frequency is increased a bit, okay, so this is low frequency, this is mid frequency, a slightly increase in frequency, then you can see that in the sampled part, the edges are a bit more jagged than before. Okay, so this effect is sort of more visible than it was before. Okay, it's still not too disturbing, but you can see sort of this pattern appearing here, right? On the other hand, if you have a high frequency signal being sampled on this sampling grid, then you can clearly see another pattern arising, right? This is an aliasing pattern. So this is a pattern which was not present in the original frequency, and now it is appearing in the sampled image. Okay, so this is how aliasing shows up in an image if you are undersampling. Okay. Now, how does one remove aliasing? So aliasing is not easy to remove, and it will probably never go away. The only thing is you can affect a little bit of blur to make the effects less, appear a bit less. Okay, so aliasing doesn't go away. The only way to avoid aliasing is by oversampling. But yeah, again, oversampling means you need to have more number of pixels and more number of samples and all that, which cannot be always possible. So anyway, so this aliasing is a thing that you should be aware of, a pattern that was not existent in the original signal, but is appearing now because of undersampling. I think there should be some in the book there will, if you just search in the index for aliasing, there might be some other picture examples of aliasing. Okay, but essentially this is what happens. Okay. So these were the 4 things that I wanted to talk about. Okay, this Laplacian, bandpass, bandreject, and these 2 patterns. Okay. So with this, I'm going to say that our discussion of the frequency filtering in the frequency domain is going to end, and we are going to move on to feature detection. Okay, and in feature detection, we will first do point, edge, and region detection. And we'll also look at thresholding. So we'll do some basics, and then we will move on to mid-level processing topic. In fact, when we move to feature detection, then we are already moving to mid-level processing. And we will talk about segmentation and some more operations. There is one topic called morphology, which I don't know if I'm going to able to cover. If I will be able to cover in any detail. So morphology or morphology operations, these are certain set theoretic operations on an image. Okay, so what I'll do is in one of I will make an assignment or small assignment with morphology operations, either that or I will try to just demonstrate morphology operations in class without really going into too much detail. So morphology usually forms part of pre-processing of an image. Typical morphology operations are like dilating, eroding. These are just or thinning, thickening, and something called as opening and closing. Okay, and these come into play especially when so suppose you have image components. So for example, eroding and thinning are quite close to each other. Okay, so if you have an image component, something in an image, and you want to reduce its size, okay, you want to reduce its size from all sides, okay, and you want to reach something like this. So this is some unwanted thing that you want to remove. Then one of the things that you will do is erode. You erode the component so that essentially what happens is the values of the pixels or the intensities at these pixels are simply set to 0 or removed. Okay, and so the result of this eroding will be this small piece that you actually want. Okay, one of the ways where eroding is useful is suppose you want to count something. Okay, for example, suppose Yeah, bottles in an image, that's an example. So suppose you have, an image of bottles stacked closely to each other. Okay, and suppose the bottle caps. So how will you count bottles? One of the easiest way to count bottles is to focus on the bottle caps. Okay, because they are different, they are the most visible part of a bottle. Okay, so suppose you have these bottles, okay, and you see these bottle caps like this. Okay, these bottles are all sorry for my drawing is not so good, but so these bottles are stacked one behind the other like this. Okay, and suppose you want to count these bottle caps. Okay, so you do your some kind of thresholding, and you change this original image to a black and white image. Okay, so if you change this to a, with some thresholding, if you change this to a grayscale image or a binary black and white image, then you'll probably see something like this, right? So you're now, it will appear something like this. But now, okay, this piece you can clearly separate out. Okay, so the first cap you are able to separate out, but these later ones you are not able to separate out so closely. Okay, for all practical purposes, if these are colored, then the black and white image might appear like this. Okay, so there isn't enough separation between these two, right? There is some separation here, so you can implement some kind of algorithm to count the connected components in this image. Okay, there isn't enough separation here, so how do you get this separation? Okay, now here you might realize that you don't require the shape of this bottle cap. You might as well just count these 4 points or 4 blobs. If each bottle cap appears as a blob, you're good, right? Now, so in such a case, to affect this gap, getting this gap between these components, one might choose to do eroding. So if you erode the image, what is going to happen is these pixels are going to get eroded. Okay, the boundaries get eroded, and each of these bottle caps will reduce to a small blob. Now it's easy to count the blobs. Okay, so this is one example where this morphological operation of eroding is useful. Okay. There might be other cases where you might want to go the other way. Instead of eroding, you want to increase. Okay. For example, there's something that I'm working on right now is, you have these, so when you go to an ophthalmologist, for example, to get your eyes checked, there is a certain device called a placebo that is kept in front of the eyes, especially if you're going for a cornea check. Then, it produces these rings that are reflected in the eye, and, the measurement tells you important information about the cornea. Now, what happens is when a patient, that image is being taken, then the eyelashes can cause gaps. Okay, so actually this appears as bands. So there is one annulus here, white. Then there is another one here. Maybe I will share one of these images with you later. And so on. Okay, so this is appearing on the cornea as some rings. Okay, and you want to make good measurements of these rings. Then what can happen sometimes is that the eyelashes can cause gaps here. Okay, so there could be gaps in these. Okay, and you want to fill out these gaps, because unless you fill out these gaps, you are not going to get a good measurement of this circle or whatever shape this comes out to be. Okay, you really need these things to be filled out. Okay. Now, in such a case, one might go for dilating. Okay, or even a combination of opening and closing. Okay, so one of these things. Then what these operations do are they fill out the gaps with whatever pixel is here. Okay. Now, one characteristic of all these morphology operations is that you will want to do a morphology operations on a binary image, which means background and foreground pixels. So always the image is broken into 2, foreground and background, done by some kind of thresholding, which means you just decide some pixels you will call background, and the other intensities you will call foreground. Okay. So first the image has to be broken up into background and foreground in this way, 2 sets. Okay. And these are all set operations. So you apply the appropriate set operations on the foreground pixels and background pixels to affect either you join gaps, fill gaps this way, or you create gaps. Okay. And all this is done so that the image quality is enhanced for further measurements. Okay, so this is like I'm just giving you a short introduction to what morphology looks like and a detail of how each of these operations work. There are many. Okay, so if you, I will give you the reference. You will see there are many such operations. These are the main ones, and one of the most important or few of the most important reasons why morphology operations are done is because you want to count connected components. This is one of the reasons. The other is you want to fill gaps. And this fill gaps can take a more wider meaning, in which case you want to do some kind of reconstruction. Okay, so the image has been hampered or degraded because of certain reasons, and you want to reconstruct the lost information simply by doing some set theoretic pixel operations. Then one will go for morphology operations.